Hello everyone, welcome to the class Earth System. The Earth is a complex system, interactive system. In this class, we will learn about the Earth system from the interior of the Earth, the core, the mantle, to the interactive surface, plate tectonic active lithosphere, biosphere, hydrosphere, and the atmosphere. After learning from this 1 month course, you will be able to explain the characteristics of the plate tectonic, explain the origin and composition of common rocks and minerals, explain how scientists determine the age of the rocks and the age of the Earth, tell the controlling factors of climate, and explain the effect of human activity on the Earth system. Today, in this lecture, the first chapter is an overview of this entire course. First, since this is an introductory level science class, I would like to introduce you what is the scientific method. The study of natural science is based on observations and experimentations. Scientists propose hypotheses to explain their data and observations. This proposed hypothesis will be further tested by others and see if it is able to explain new data and predict the outcomes of new experimentation. If it was not, then we will need to revise or discard the hypothesis. If it passed the test, then we can elevate the hypothesis to the status of a theory. A theory does not mean that it is 100% proved right or cannot be challenged, but it is able to explain some aspects of the nature. For example, the Big Bang theory is a theory that is broadly agreed, and it is able to explain and predict a lot of observations of the universe. However, according to the Big Bang theory, the time and the space started with the Big Bang. We do not have any solid evidence to prove it is right. So, a theory, though it is broadly agreed, it does not necessarily be 100% right, but it must be testable and subject to further revision. A scientific model is based on many hypotheses and theories. People who study models have a very popular saying is that all models are wrong, but some are helpful. So a scientific model is able to help us to reveal certain aspects of the nature, but it is also subject to challenge and will be revised or discarded as science advances. Now let's talk about what is geology. The number one difference of geology from other branches of natural sciences is that geology studies the processes that operate over long periods of time, usually in millions of years, which is the geologic time scale. And the studied processes are often in a large scale, very often in a global or continental scale. Therefore, we geologists use both method of field observations and laboratory experiments. Most of the time, field observations provide us snapshots of geologic records, and the laboratory experiments, they help us to understand the process that resulted in the records, though they cannot replay the geologic processes that operated over millions of years. To study geologic processes, the number one principle is the principle of uniformitarianism, or we can summarize the long name of the principle into one sentence, which is the present is the key to the past. The present is the key to the past. This is the fundamental of geology, which means that all natural geological processes of today works the same way in the past. The simple example will be like water flows downward, heat transfers from the warm to cold, and the gravity force points downward. A more complex example will be like The Permian Basin was filled up in a similar way as the modern deep marine basins. Geologists are curious about to figure out what makes the Permian Basin different than others, so to make it the biggest and the most productive hydrocarbon field of the United States. This involves studying the sediments preserved in the Permian Basin and to interpret the ancient depositional conditions based on the observation in the present world. For example, at present, the warm climate enhances biodiversity in the ocean and increases the organic matter in the sediments. So, warm climate must have been associated with the Permian Basin during the ancient time. By figuring out what are the controlling factors to make the Permian Basin so unique, we may have a chance to find another hydrocarbon field like Permian Basin. This is how we use the principle of uniformitarianism. The present is the key to the past as a guideline in geology to contribute to the science and economics. To be clear, geology is not governed only by uniformitarianism. In contrast, catastrophism also plays an important role. The Earth is also significantly influenced by sudden, short-lived events such as a crater impact. We know that the major extinction happened during the end of Cretaceous that killed all dinosaurs is because of a crater impact, which is short-lived, sudden, violent event that influenced globally. The next basic about the Earth I want to introduce to you is the shape of the Earth. We know that for a very long time humankind believed that the Earth was flat until the ancient Greek scholar Eratosthenes showed that the Earth was spherical. The following video explains how Eratosthenes estimated the circumferences of the Earth.
In the mid-20th century, we began launching satellites into space that would help us determine the exact circumference of the Earth, 40,030 kilometers. But over 2,000 years earlier in ancient Greece, a man arrived at nearly that exact same figure by putting a stick in the ground. That man was Eratosthenes, a Greek mathematician and the head of the Library of Alexandria. Eratosthenes had heard that in Syene, a city to the south of Alexandria, no vertical shadows were cast at noon on the summer solstice. The sun was directly overhead. He wondered if this were also true in Alexandria, so on June 21st he planted a stick vertically in the ground and waited to see if a shadow would be cast at noon. It turns out there was one, and it measured about 7 degrees. Now, if the sun's rays are coming in at the same angle at the same time of day, and a stick in Alexandria is casting a shadow while a stick in Syene is not, it must mean that the Earth's surface is curved. And Eratosthenes probably already knew that. The idea of a spherical Earth was floated by Pythagoras around 500 BC and validated by Aristotle a couple centuries later. If the Earth really was a sphere, Eratosthenes could use his observations to estimate the circumference of the entire planet. Since the difference in shadow length is 7 degrees between Alexandria and Syene, that means the two cities are 7 degrees apart on Earth's 360-degree surface. Eratosthenes hired a man to pace the distance between the two cities, and learned they were 5,000 stadia apart, which is about 800 kilometers. He could then use simple proportions to find the Earth's circumference. 7.2 degrees is 1/50th of 360 degrees, so 800 kilometers times 50 equals 40,000 kilometers. And just like that, a man 2,200 years ago found the circumference of the entire planet with just a stick and his brain.
In the modern time, studying the shape of the Earth and the dynamic change of the shape becomes a new branch of Earth science called geodesy. Not only mapping the shape of the Earth, geodesy is also studying the spontaneous change of point locations, which is the application of GPS. It's also studying the instant change of the shape of the Earth at certain point. Therefore, geodesy is used to predict a landslide in many places on Earth and saves a lot of lives. After talking about the shape and the size of the Earth, now let's see the internal structures of the Earth. The Earth is a layered Earth. Based on the density and the composition, Earth can be divided into crust, mantle, outer core, and inner core. Crust is solid and rigid. It is the lightest compared to the other inner layers of the Earth. It is enriched in silica and oxygen. The continental crust is about 2.7 gram per centimeter cubic. The oceanic crust is a bit denser, about 2.9 gram per centimeter cubic. The mantle is also solid. It is enriched in silica, oxygen, and magnesium. The mantle is denser than the crust, but lighter than the core. It is about 3.5 gram per centimeter cubic in the upper mantle, and the density increases as it goes deep to the mantle, which can reach about 5 gram per centimeter cubic. The upper part of the mantle is solid and rigid too, but the deeper part of the mantle is ductile and viscous. Though it is solid, but it can flow and convect. The turnover cycle of the convection of mantle is about 500 million years. The outer core is liquid and denser than the crust and the mantle because it contains significantly more iron than the other two outer layers of the Earth. The density of outer core is 10 to 12 gram per centimeter cubic. The Earth's magnetic field is generated by the flowing of the iron-nickel-rich outer core. The inner core is also iron-nickel-rich with a high density, but it is solid because of the high pressure in the center of the Earth. The density is about 13 gram per centimeter cubic. This is the layer division based on density and composition. The crust and the mantle can also be divided in a different way based on their mechanical properties. And the layers are lithosphere, asthenosphere, and mesosphere. The lithosphere including crust and the upper brittle part of the mantle. The asthenosphere is the middle ductile part of the mantle, and the mesosphere is the deeper part of the mantle. The following video animation shows the differences and the connections of the two ways of dividing the Earth layers.
Our Earth is made up of layers, and there are two types of layers we need to learn about in order to understand plate tectonics: the compositional or chemical layers and the mechanical layers. We could spend an entire session on what makes both of these types of layers unique, but for this lesson, we're simply going to provide an overview. There are three primary compositional layers to the Earth's surface, and these are probably the ones you're most familiar with: the crust, the mantle, and the core. It's important to understand that the compositional layers refer to the materials or elements the Earth is made of. However, if we take a look at how the inside of the Earth behaves, we can divide them even further into mechanical layers. Starting from the outside working in, the lithosphere is the outermost layer of the Earth, which contains the entire crust and the topmost layer of the mantle. The asthenosphere contains the same materials as the top layers of the mantle, but the pressure and the heat are increased. It's not exactly a liquid, but it does move like heated rock, so you could say it's somewhat fluid. The mesosphere is next. At this level, the pressure is really starting to build, which restricts the molecule's ability to move, thus making it very, very rigid. Past the mesosphere is the liquid outer core. Extremely high temperatures melt the metals contained in this layer into liquid form. Think flowing rivers of lava, and you'll have a pretty good idea of what the outer core is like. And finally, we reach the solid inner core. Just like the liquid outer core, the inner core has extremely high temperatures and is composed of mostly metals, which might lead you to ask, why isn't it liquid as well? The answer is pressure. There's so much pressure at this depth that even though the temperatures are beyond the melting points of the metals contained in the inner core, The high pressure essentially squishes everything down into a solid.
The boundaries between lithosphere and the asthenosphere and between the asthenosphere and the mesosphere can be clearly visible when waves that generated by earthquakes and explosions, also called seismic waves, transported through the earth. The seismic waves transport in different speed in the lithosphere, asthenosphere, and mesosphere. We can see the speed jump at the boundaries. After talking about the shape and the internal layered structure of the Earth, now I want to show you that the Earth is an interactive system. The radioactive decay activities such as the decay of uranium and thorium inside the mantle and the crust generated heat, and the heat drives the convection of the mantle. The convective motion of the mantle drives the plate tectonics by dragging and moving the lithosphere. Moving the lithosphere resulted in rifting and colliding plates of continent as well as the oceanic plates. It makes valleys, ridges, and mountains of the Earth. Changing the topography of the Earth will change the atmosphere's circulation and change the climate. The climate is also simultaneously influenced by the radiation from the sun. Therefore, you can see from inside out, the Earth is a very interactive system. In the last part of this lecture, I want to show you an overview of the geologic time, which is the history of the Earth. The Earth is formed 4.6 billion years ago and spent a long time to develop continents, lives, and the modern atmosphere. It is hard to talk about the large numbers of years and make sense how long it takes the Earth to evolve and make it just perfect for us to live in. I want to show you the following video, which turned the history of the Earth into 24 hours. It gives a better sense how long it takes creatures to evolve and when our humankind came in play.
Our planet Earth formed about 4.5 billion years ago. That's a really long time ago. To help picture it, imagine the entire history of the Earth squeezed into just 24 hours. Reducing Earth's creation to a clock may seem like a strange thing to do, since so much of what happened took a lot more time than 24 hours. According to research scientists, it gives us a picture of what kind of pause may have taken place between the events that formed the picture of life as we know it today. When we think of time in this way, humans have only been around for only 78 seconds. Formation of Earth. Earth and planet. Results in the moon. Meteorite bombardment. Origin of life. Oldest fossils. Abundant Bandidium formations. Great oxygenation event when oxygen was no longer captured by oceans or land. So begins a significant increase in the atmosphere. Single-celled algae. First sexual reproduction. First seaweeds. First jellyfish. First land plants. Coal swamps. First dinosaurs appear. First mammals appear. Last mass extinction, in which dinosaurs disappear. Humans. Modern humans.
Okay, so this is the first lecture. I hope you enjoyed this lecture. Please use the lecture slides to review before taking the quiz.